I have some vector field in space, okay? I have some vector field. Is that okay? I have some vector field here. So let me choose some coordinate, okay, for my comfort, okay? I will choose some point A here. I'll choose some other point B in space, okay? And I will draw a path from A to B. I will draw a path from A to B. Is that okay? I have 2 points in space. I will draw a path from A to B, okay? Now what I do is, along this path, I'm going to imagine infinitesimal line element. Can you see this one?
Yes, sir.
Yes, I'm going to draw infinitesimal length element, line element, what we call DL vector. DL vector. Is that okay? So at each and every point, what I do is, okay, at each and every point, I'm going to take what you call dot product of my vector field, okay, V. I'll call this vector field as V, okay, with this DL vector. With this DL vector. Is that okay? This is DL vector. Okay, suppose if you take any point here, you have DL vector here, okay, you have V here. At each and every point of that line from A to B, let me call this one as A, this one as B, okay. You can represent a point by what you call a kind of position vector, okay. You can call point by a position vector A, okay. Let me call this one as a position vector of this point, okay. A vector is a position vector of this point. Like that, B vector is a what you call position vector of point B, okay. Let me say like that. Now look at here. What I do is, along that path, I'm going to take my what is DL vector? Infinitesimal displacement vector, okay. I'll take that one, and I'm going to take dot product with V, okay. What I do is, I'm going to take V dot DL. I'm going to take this dot product at each and every point along that line, and then I'm going to integrate. Is that okay? Then I'm going to integrate. But A vector is a position vector of point A. B vector is a position vector of point B. Position vector means vector from origin to that point. I hope you know that one, okay? We call this one as line integral. Line integral of a vector field from A to B along this path. Look at here. From A to B, you have infinitely many paths in space. Okay. Line integral from A to B along this path. Can I name this path as some P? Put some P somewhere here. Are you getting a point? Because from A to B, you have infinitely many paths. You have chosen one of those infinitely many paths, okay, and you have taken line integral. That's how we say. Without what you call mentioning this path, that line integral would be meaningless actually. Are you getting a point? Yes. That doesn't matter. It may have divergence, it may not have a divergence. That doesn't matter. This is the most general thing that I'm. It may be uniform, non-uniform. It doesn't matter. But at each and every point, you can define what you call dot product between vector field and what you call your line element. Suppose if you take DL vector here, so DL vector, okay. So here you have your vector field somewhere in this direction. Is that you take the dot product at each and every point. You have taken dot because vector field is a function of space. Am I right? You take a dot product and you integrate this scalar. This after taking dot product, that's a scalar. Am I right? Integrate that one. We call it as a line integral. Okay. To define line integral, you have to define a path now, because between any 2 points, you have infinitely many paths. Isn't it? Between any 2 points in space, you have infinitely many paths. You can go in any way, isn't it? That can be either uniform or non-uniform. I'm not quoting that one, okay? This can be uniform or non-uniform. Why are you worrying that one? This is some vector field. It's a function of space. What happens if it is uniform? You tell me. It doesn't matter. Is that okay? I'm talking about most general definition of line integral. Is that okay?
Sir.
Yes.
Sir, like we take in ampere circuital law types of
Wait. Don't go further. Ampere circuital law, again similar to that. Look at here. Similar quantities I'm going to define here. Okay. Now look at here. So what we can do is we can go in space and we can come back to the same point. Okay. We can take a closed. Okay. We can take a kind of closed what do you call line. Okay, we can take a closed line. You can take dl at each and every point. Okay, you can take a dot product again. Speak out. Is that okay? You can take a dot product again. You can have a closed path, isn't it, in a space. So then we are going to draw that line integral like this, closed path integral or closed line integral of v bar dot dl bar. In this case also you have to define closed path. In space you can have infinitely many closed paths. Or if you take this point C, okay, this point is C from the origin, okay. So from C you can go anywhere and you can come back to C, and there are infinitely many closed paths like that, isn't it? You have to define a closed path. So we call that one as closed line integral. Line integral or path integral, okay? Closed line integral or path integral, just like closed surface integral, am I right? Open surface integral, closed surface integral, isn't it? Now look at here, whenever you have closed path integral, again, whenever you have a closed path, you have two choice of taking dl vector. Either you can take dl vector like that or dl vector opposite. Okay, you have two choices. Just like in case of surface integral, you had two choice of dA vector. Am I right? Here also, in case of closed path, two choice, isn't it? Inward from the region, outward from the region for a closed surface, isn't it? Like that, you can take your dl vector anti-clockwise or clockwise. Okay, that you have a choice. Okay, you have a choice. Wait a second. Now look at here. So this closed path integral, okay, this closed path integral of a vector field, okay, v bar dot dl bar, that's how we say this closed path integral, okay, we call this one as, we have a name for that one, circulation. It is called as circulation. The value of that integral is called as circulation. Why they might have called that one as a circulation, am I right? We shall see that one. Is that okay? Now I have a uniform vector field. Let me take a uniform vector field. Okay? Let me take a uniform vector field. Vector field is uniform. V is equal to V naught into x cap. Is that okay? Now let me take a closed path. Let me take a closed path. Small path, is that okay for you? Is that okay? Now I'm going to take path integral like this. Closed path integral, okay? Along this path from here to here, you have dot product cos 0, am I right? And that is positive. Along this one, vector field is like this, am I right? This is the direction of vector field that I have taken, okay? This is the direction of vector field, okay? Along this path, okay, it is 0. Along this path, your dot product is negative. If you take this length as L, okay, this length of this one as L, okay, along this path, if you do V dot dl, okay, so if you do that integral from here to here, this point to this point, can you just point out? Okay, so from this point to this point, what you will get is again, so you will get V naught into that length itself, because cos 0 will come. So if you do that integral from this point to this point, actually, your dl vector is opposite to your vector field. You'll get minus V naught into L actually from here to here, where L is the length of this one. Is that okay? As a result, look at here. Again, as along this line and along this line, your dl vector is what you call perpendicular to your vector field. That dot product vanishes. Is that okay? So that the total what you call line integral will be 0. Now we say circulation is 0 in this case. Why? Our vector field is not circulating, it is going parallel to each other. Are you getting my point? So that's why this closed line integral is a measure of how much circulation our vector field is doing. Here our vector field is not doing circulation at all. Is that okay? It is going parallel and its strength is constant. It is a uniform vector field. Vector field, so think about vector field, it is not circulating, isn't it? It is going parallel to each other. So that's why we say circulation is 0 for this vector field. Wherever you take circulation is 0. Wherever you take this kind of closed integral, you will have closed line integral 0. It need not be squared. Here I have taken squared shape because it is simple. Am I right? It can be any shaped closed line integral. You will have a closed line integral 0. Here for simplicity I have taken square. Is that okay? What are you thinking? No, don't go further. You read out later, okay? Don't go further, okay? Yes. Circulation is 0 here, okay? Suppose I have a vector field. Magnetic field due to current element, isn't it? Now in this kind of vector field, look at here, again you can take square shaped what you call you can either take square shaped closed line integral or curved shaped. It doesn't matter, okay? Even if you take a kind of square shaped what you call closed line integral, okay? If you do this one, you will get this closed line integral non-zero in this case, okay? In this case, so suppose if this is the vector field, closed line integral of v bar dot dl bar, which is non-zero about this point actually. Again, that should be taken about this point, okay? So this should enclose this point actually, point of circulation actually. If it doesn't enclose that point of circulation, what would happen? Yeah, anyway, we shall think of it one, okay? So this closed line integral is called as circulation. Can you just again, so take one what you call, so take one line integral where your path runs what you call as a circle, okay? Then definitely at each and every point you have cos 0, dl and v. Again, this dot product will be what you call positive and it's going to add up, isn't it? I have taken vector field like this. These are the vector field direction, okay? Speak out. Just like our magnetic field due to what you call current carrying wire. Is that okay? No, don't think about divergence. Wait a second. Don't think further, okay? Wait a second. Try to develop the idea, okay? So like that, look at here. Not only these kind, again, it need not to be, the direction need not be like this, okay? So what happens is, suppose if you have a vector field, okay, V is equal to V is equal to, okay? Let me take this one as Z axis, okay? Z into X cap. So then how do you draw that one symbolically? Is that okay? Along Z axis, you have to increase what you call density of field line, am I right? Vector field direction is along X cap, okay? But along Z cap, its strength is increasing. Can I draw like this? Speak out. Speak out. Now if you take a circulation, okay? If you take a circulation, what would happen here is, okay? If you take a circulation, so you will have circulation non-zero. Circulation means closed line integral, okay? Circulation means closed line integral. Look at here. Here you have what you call high, your vector field strength is high here. Okay? Here vector field strength is low here. Look at the diagram. Look at the diagram. Vector field strength is high here. Vector field strength is low here. Isn't it? When you take a dot product, suppose L is the length of this one. Okay? So you will have what you call some V1 into L here. Okay? You will have some V2 into L here, where V2 is lesser. Okay? I can't show this one here. I've shown only one field line, okay? But actually your field strength is low here. If you move along Z axis, your field strength is increasing. That's how I have taken, am I right? So that's why when you take line integral here, line integral along this path is more than line integral along this path. When you take the circulation, you will get some what you call, I think this is high, this is low, negative part is low, so that you will get some positive circulation here. Is that okay? You will have, even though vector fields are parallel to each other, you have some circulation here. Speak out. You are not seeing that this one, V is equal to Z into X cap. It is increasing along Z axis. Whatever V you draw here, that has a more strength than whatever V you draw here. Is that okay? Wait a second, I will get into the curl. So this whole energy, whatever I am spending, so that I can define Gauss theorem and Stokes theorem easily, so that I don't have to prove that one. Is that okay?
Sir?
Yeah. Yes, speak out.
Sir, mainly circulation means whatever field remains after integral, sir.
I mean, this is circulation means closed line integral, value of the closed line integral, and that is non-zero. Compare these two. That is non-zero here, and that is positive here because you have high field strength here. Okay, this is higher, this is quite lower. So that's why this, again, this dot product will give negative actually, this line integral. And anyway, these two will not contribute, okay? You don't have to take these two. These two will not contribute. So the net circulation is positive here. Is it okay? You have a net circulation here. Is that okay? So this is how you can think of circulation of a vector field. Even though vector fields are parallel to each other, you have some circulation here, okay? Circulation means closed line integral is non-zero, okay? Now look at here. You have some vector field. Divergence is 0. But curl exists. That's what I want to write, okay? Let me take a, what you call, symbolic vector field here, okay? Symbolic vector field here, okay? Now what I do is I'm going to take infinitesimal, okay? I'm going to take infinitesimal closed line. Is that okay? And I'm going to take line integral of the vector field around the infinitesimal, very small closed loop, okay? And what I do is, along when I make it very small, I can define a surface area enclosed by the loop, isn't it? You have a loop, okay? When you make that loop very, very small, okay, even though whatever the shape of the loop, okay? Whatever the shape of the loop, what you can do is you can define a planar area enclosed by the loop actually. Is that okay? Now what I do is I will use my right hand thumb rule, okay, to define one area vector or to define one unit vector, I'll call it as n cap. Is that okay? If my line integral, okay, if my line integral of vector field, okay, if my line integral of a vector field is running like this through, again, if my dl vector, okay, these are the dl vector, am I right? If my dl vectors are running like this, okay, so then my thumb will represent the direction of the area vector. Let me define one area enclosed by that loop, okay, and let me define an area vector for that, okay, and it has some area A, okay, it has some area A, and that area vector I can write as A into n cap. Is that okay? And I'm going to take circulation of that one, okay. So then what I do is I'm going to divide by magnitude of area vector or area, and I'll put limit area tends to 0. I'll put limit area tends to 0. That means I will make it as small as possible. Is that okay? Then, so that is equal to, look at here, curl of a vector field, curl of, again, once you make area tends to 0, you can define these stuffs at some point, am I right? We can call it as a curl of a vector field taken dot product with n cap. So this is a mathematical definition of a curl of a vector field. Is that okay? Taken dot product with unit vector along area vector. And you have you have a relation between this path integral and this n cap, okay? If path integral runs along your forefinger, your thumb will represent the area vector, okay, or n cap direction. So that is the convention that I have used here, okay. I hope try to grab this point. So now, can I take this one as circulation per unit? This is circulation, okay. This is called as circulation, this closed line integral, okay. Can I take this one as circulation per area? Circulation per area. Speak out. Circulation per area, because you have divided by area. This is called as circulation. This is called as area. Circulation per area. Can I call like that?
So I want to say, whatever we divide the area, I mean, if it will shrink or it will increase, will it?
No, I put limit A tends to 0. But first see this one. First see this one. Circulation per area, isn't it? Why are you struggling? No, you don't think beyond, okay? Look at here. I have to direct you towards some thinking. Are you getting my point?
We divide that with the volume, right?
We divided by volume. This is a different story. I'm saying take it as it is. I mean, I can't prove this one, okay? I can't go for mathematical proof. Is that okay? Take this one as a definition of a curl. Now, in that definition, I have defined something, isn't it? So, this is a circulation per area, okay, for infinitesimal area around the point in question. That's equal to curl dot product with n cap, area vector direction. Why I have done this one? Can you guess this one? Later I'll take area to that one. I'll do surface integral and I will enlarge this one. That will become your Stokes theorem. Is that okay? That's what I'm doing here. Also, Wikipedia. Yes. But write down the mathematical expression, think over it. You can grab that one, am I right? Because these are the evolution, are you getting my point? It's not like something strange is defined in between, am I right? You know what is this dot product? What again, you can imagine, am I right? I have shown how this talks about circulation, actual circulation of a vector field. We call this in a circulation, am I right? Now I told by some example, it will talk about how our vector fields are curling, isn't it? Are you getting my point? This value.
So I have to say one example. I mean, in the when water removes.
Yeah, again, when water swirls, there again your what you call velocity field, okay?
These kind of fields are
So then again, if you take a line integral of that velocity field around a closed loop, you will get non-zero. We call that as circulation. That is mathematically called as circulation, this closed line integral.
That's what I got there. But if you divide it by area,
You made it per area.
what about the surface it creates?
Hmm.
I mean, in that surface, in that loop, divided the area, it is produced that curl, I mean, same or different?
No, it's not. This is producing this curl. Mathematically, this is equivalent to this one. That's what I'm saying. Circulation per area or closed line integral per area, when you make that area as small as possible, infinitesimal, then you can talk about a point in space. Am I right? And so that is equal to curl taken at that point, taken dot product with n cap, where n cap is the unit vector. Yeah, speak out.
Sir, so sir, here we didn't take any line integral, sir. Sir, we took any objects here in that field surface.
Where we have taken line integral.
But sir, area vector along that line integral surface is not getting, sir.
Area vector is not along that line integral. I have taken what you call area enclosed by that line integral. So then I defined the area vector. Are you getting my point? I defined the area, a planar area. Yeah.
You took any area, then you define the line integral about that.
No. First I will take the line integral, then I define the area.
Okay, sir.
I'll start with this one, then I define that one. Is that okay? So that's why, yes.
Sir, curl around here, sir, curl around, sir. Direction is area vector direction.
No. Curl direction is not, I'm not saying that one. So did I said like that? No, isn't it? What I'm saying is these two are mathematically equal. That's what I'm saying.
No, the clever part is if I do Stokes theorem.
No. Later, I will convert this one into Stokes theorem. Okay. And one more thing, you haven't seen the, what you call, the interpretation that I have done on this closed line integral. You haven't concentrated on that one. If vector fields are curling, this closed line integral gave me non-zero value. That means it's a measure of something, isn't it? It's a measure of how our vector field is circulating actually. That's why we call that in a circulation. That's why some mathematician defined this one as a circulation, this closed line integral. Is that okay? And now I am shrinking that closed line integral to very small infinitesimal closed line integral, and I am defining what you call area enclosed by that closed line integral, and I am defining what you call area vector. Okay, so mathematically these two are equivalent. Is that okay? Speak out. Where we call this one as curl of a vector field. So shall I move on? That's why curl of a vector field is a measure of circulation actually. We can call it as a circulation density. Curl of a vector field at some point is equal to circulation density. Is that okay? But you should define what is that circulation, just like we defined outward flux, am I right? Earlier we have defined closed surface integral of V bar dot dA bar, am I right? We defined this one as outward flux, am I right? So like that, you have to define it as a circulation, because this was a measure of vector field line which is going outward from the region of the surface. This is a measure of how much our vector field is circulating around a point in question. Yeah, speak out.
Sir, circulation is scalar, sir.
Yeah, obviously.
Yeah.
Flux was also scalar. Circulation is a measure of something. It's not a vector. It's a scalar. This whole thing is a scalar. Once you take dot product, vector is gone. Okay?
Curl is
Here.
That dot product is just.
Scalar divided by a scalar is
This is not a vector. You have taken dot product, right hand side. See that one.
Sir, mainly, sir, here circulation of the vector product, dot product, in LSS part is, sir, vector, a scalar divided by a scalar, how to represent, sir, here n cap direction is?
This is a dot product between two vectors. This is also scalar.
Oh.
this is is the condensing part.
So now what will happen is sometimes, okay, so you suppose you said your water is circulating here, okay, but if you take your what you call closed line integral vertical, suppose horizontally it is circulating, but if you take closed line integral vertical, then your area vector will be like this, isn't it? So then that dot product between that one, that will be 0 actually. If you take this kind of what you call, you will not have circulation over there actually. Let me try to define this one later. Water is circulating like this, but you have taken line integral vertical. Water is circulating horizontal. If you take a line integral vertical, then you will not find any circulation. I mean, that line integral will be 0, okay? If you have a horizontal circulation, if you take horizontal line integral, you will get non-zero. Is that okay? So that's why this dot product is also very important. Is that okay?
Collection will be
Yes, it is important actually. Now, actually, fluid dynamics people will use these things very much. We don't need too much here. Now, curl of a vector field, am I right? That's again a vector, okay? So we define it like this. It's a kind of operation that you can do using what you call your del operator, okay? Suppose if I define that vector field as Vx into x cap plus Vy into y cap plus Vz into z cap, okay? Then curl of a vector field. So it is defined like this, okay? Look at here, Vx, Vy, Vz, those are function of x, y, z, okay? Vector field I'm talking about, okay? X cap, y cap, z cap, okay? Dou by dou x, dou by dou y, dou by dou z. Is it okay? Vx, Vy, Vz. So that means this is equal to x cap into dou Vz by dou y minus dou Vy by dou z minus y cap into dou Vz by dou x, okay, minus dou Vx by dou z plus z cap into dou Vy by dou x, minus dou Vx by dou y. Minus dou Vx by dou y. Minus dou Vx by dou y. Now look at here, this contains derivative of, suppose look at here, there is no x component derivative with respect to x, there is no y component with derivative with respect to 1. X component derivative with respect to z, x component derivative with respect to y. Component of a vector along x axis, but derivative with respect to other two variable. That's how, again, this whole thing is composed actually. Is that okay? Speak up. Now again I can give the two definitions. One definition I have already given, okay, earlier. The second definition is, okay, can you write down? Curl of a vector field is a measure of, how much a vector field circulates or curls around the point in question. Around the point in question. That is one of the definition. Other definition, you can take curl of a vector field, okay, take a dot product with n cap, okay, that's equal to circulation density, circulation per area, okay. That's the other definition. So we have already taken, okay. It's a measure of how much a vector field circulates or curls around the point in question, because these are derivative, okay, kind of derivative. You can take curl of a vector field at some point, okay. Now it will add like a vector, that's why it's a vector, okay. Curl of a vector field is again some other vector field. Is that okay? Speak out. Curl of a vector field is again other type of vector field. Yes.
And you have talked before the curl of the vector at any point called the circulation at that point. So, in case of a fluid or a water, the volume of the water where it is sinking in some places. So the strength of that curl, the heat of the water means how speedily it goes into that curl.
Now look at here. You can have water and you can swirl that one, am I right? You can swirl with low velocity, very low velocity. Then the circulation is low, because velocity fields have low strength. If you swirl with more velocity, then your velocity field have more strength. And circulation is more, because closed line integral will be more. Closed line integral depends on that velocity vector field, am I right? That vector field also.
No, sir, it varies maybe. It may be varies. Because
No, I have taken circulation.
uniform
Not again. It need not be. It will not be uniform actually in case of water,
in the sense that
because you have what you call not surface tension. What is it? Resistance between the layers of the water. Am I right? What we call viscosity, isn't it? It's a viscous fluid. That's why that velocity, that magnitude will not be constant. Okay, it will vary radially. But what I'm saying is, if you swirl with a very low velocity, then we can say circulation is low. Think about vector field, velocity vector field. Its strength is low. Depends on magnitude also. Am I right? Yeah.
Sir, it is like when we throw a stone on a pond, then the circulation means the velocity
No.
of that
When you throw a stone on the pond, it's a kind of crust or trough which will move away. Okay, there is no what you call swirling kind of motion of the water molecule.
can you say one thing? Willful. If I will
Yeah, again. So there only I'm talking about circulation. Suppose, so again, you have a beaker, okay? You somehow made the circulation, okay? So that again your water is what you call, it will make this kind of shape, am I right? It will make this kind of shape. It will swirl, am I right? Yes.
Whether this concept are applying the cyclone, the motion of the cyclone, and the strength of the cyclone.
Yeah, definitely. Now, strength, that depends on what you call, how much it curls, as well as it depends on the strength of the vector field, isn't it? Yeah, definitely, it can be done. No, these mathematics, okay, these have very wide applications, okay. I mean, we can't, maybe, I don't know, this may be even applied to some, what you call, universe or some, the study of some galaxies or something, isn't it? Who knows, am I right? But mathematics, I mean, again, just like he said, for cyclone, isn't it? For the study of cyclone. Not only that, these things, this vector calculus is used to do a very good animations actually. A kind of, what do you call, how to say? We call it as abstract art. Is that okay? I think you might have seen there will be some fluid which will slowly move on. That kind of what you call screensavers, which are made actually in a computation using again vector field idea. Is that okay? Yes. So try to grab that idea. Okay. Now let me take one simple example, and then I will close the class. Okay. We shall continue in the evening, but you will have some homework here. Okay. Suppose if you have a vector field like V naught into x cap, okay, then del cross V is equal to 0. You can show that one. Suppose if you have a vector field that's equal to x into x cap, then also curl is 0. Check this out. If vector field strength is increasing along x-axis, okay, then also it will not have any curl, okay. Strength is increasing along x-axis, okay. Strength is increasing along x-axis. Is that okay? Then also it will not have curl. Suppose if it is a uniform vector field, it will not have any curl anywhere. Is that okay? You can think like that. You take it as a water fluid, okay? Fluid which is moving. Take it as a velocity field, okay? It's very difficult to have that velocity field of a water uniform because of that, what you call surface tension. It's not surface. Why surface tension is coming? Viscosity. So there's a kind of resistance between the layers, okay? So because of that, what will happen is, if you have a water which is going, okay, over the surface, it will have one velocity. Inside, it will have other velocity. It's very difficult, but just think like that, okay? Now look at here. You just have one more idea, okay? One more idea. So suppose water is moving so that its velocity field is very uniform. You made it like this somehow, okay? You keep a ball inside that water. Sphere inside that water, ball. Then what this ball will do, this ball will move like this, am I right? And that ball will not, rotate. It will not rotate, it will have only translation motion. Is that okay? Suppose if you make this kind of vector field, V is equal to, okay, let me take Z cap. Z into x cap. Now find the curl. Curl will be non-zero. Think of curl equation, okay? It contains x component, z derivative, okay? It contained x component and z derivative, isn't it? Speak out. Now look at here. Curl is non-zero. So in this case, what will happen is, look at here. Along z axis, your vector field strength is increasing. Am I right? Are you getting my point? Speak out. So then what will happen is, at one side of this ball, you will have one velocity, and other side of the ball, you will have other velocity of the water, okay? Then what will happen is, this will start rotating that ball. If velocity differs at two sides of the ball, just concentrate on this one. So that's why again, so I am talking about one physical situation here. If you place a ball, if suppose your velocity differs, okay, along this axis, then what will happen is, along with linear motion, it will, rotate actually. You can feel that one. Isn't it? Can I say like this? There is just imagine a water flow, okay, and you place a ball. In this case, or in this case, or in this case, if you have a vector field like this, that ball will not rotate at all. It will have only linear motion. Is that okay? Because again, what will happen is, if you place a ball here, whatever the velocity of fluid here is same as velocity of fluid here, it will not experience a net torque actually. But here you will have higher velocity, here you will have lower velocity, then it will start experiencing some torque, it will start rotating.
Then you can say difference of force upper or lower.
That force will differ and net torque will exist and it will start rotating. So that's why that placing a ball, a small ball, you can measure how much curl exists of that vector field actually. Is that okay? Okay, this may generate a new idea, isn't it? Suppose if there is any problem where you want to measure a curl practically. Okay, I gave you one idea. That idea, how did that idea came? Okay, this may be idea which may be valid or not valid, but idea came, isn't it? How did that idea came? By the understanding of this mathematics only, isn't it? Are you getting the point? Now, if somebody asks, how do you measure a curl, isn't it? I will give this example. And who knows, okay, if you develop that one, this may become one, very good idea for the measure of the circulation, isn't it? We got.
It's already in mathematics.
Sir,
Yeah, it may be there, isn't it? Now look at you. But I didn't know that one. But I generated that idea because this understanding of the mathematics have that power actually.
I have studied that one.
Hmm.
sir,
Yes.
Magnetohydrodynamics.
In
that all those
Yeah, again, people might have done whatever the idea you generate. So maybe before 10 year or before 20 year, you may find somebody else have done. But you have to keep thinking in that way. Then you can generate a unique breakthrough, isn't it? Yeah, speak out.
and sir, in both cases, we can compare this curve with the closed integral also, sir.
Definitely. That is mathematically related to closed line integral of a vector field. Definitely. Okay. So why you need to think? Yeah, speak out.
Sir, in lower diagram, you have made a bond. The density of the line representing the density of the material.
No. I have increased the density of field line to show that field strength is increasing. Okay. But I have to take infinitely many field lines actually, but I can't do that one on the board. But what I know, again, at this side you have low field strength, at this side you have high field strength, or at this side your velocity of this water, if you take it as a water, it is low, this side is high, so that it will experience a net torque.
So, sir, it will rotate in an anti-clockwise direction.
This is more, am I right? Yeah, it will rotate, no, clockwise, isn't it? This is more, this is less, then the net torque will be like this, isn't it? But here there will be no net torque because here also velocity is same as this one, isn't it?
Sir, in second case, we can say it is a boat and river problems which we can do in class 12, sir.
This one we do in class 12. No, we don't count any circulation, okay, or rotation. We just find velocity of that one or something, how much time it takes to fall, isn't it? Viscosity, to find the viscosity of the fluid, isn't it? But I'm talking about how much it rotates, am I right? If it rotates more, that means you are, this has more velocity compared to this one. That means it has a more curl, am I right? You can say like this.
Yes, sir. We can also see that just like if the river is in flow, if there is a fluid and river, all the obstacles between them, they are just moving to the river, which they are moving clockwise direction, and from the high density, they are turning to the low density, the shore area or what.
Yes. I mean, in case of river actually, again, when you go to the banks also sometimes velocity changes. When you go deep also velocity changes actually. I think in the deeper side it has a less velocity, isn't it, compared to the top side. And I heard in the for the river of Ganga, that difference is very low. I don't know. Okay. Sometimes about these things people bluffs actually. Okay. For river Ganga, I mean, but that is quite illogical, isn't it? Because that's also water only, H2O only, isn't it? Maybe more polluted. That's a different story. Now look at here. But when you go down, some people said like that. I don't know. We have to do fact check. No? Yeah, all rivers are same.
Water, sir.
No, who knows the this salty thing? This the
Maybe some effect may be there.
how to say, because it came from different land, isn't it? Whatever the content, that also decides the viscosity actually. I mean, I don't know, but some people said like that.
That may be happen.
So that's why the Ganga digests more, even though we try to pollute more. That's how somebody is told, that maybe either bluff or right, okay?
So polluted.
Because many people will always try to come out with some scientific reasoning for whatever happens, isn't it? Yeah, that's a different story. So grab the point. I think you can solve some problems here. Gradient, I hope you have solved the problem. On divergence, you have 1, 2, 3, 4 problem, and for curl couple of problem. Again, today also you don't have much problem. Okay. I will give the homework in the evening together with the line integral and surface integral. Yeah, speak up.
Sir, if curl of a vector field is equal to 0, then vector field is conserved like that idea.
Yeah, we call that one as conservative force field actually. If force field is curl is 0, I'll come to that point. Okay. Conservative field which will have a curl 0. So actually that conservative, that word that came from line integral only. Okay. Closed line integral is 0 actually. Okay.
Sir,
Yes.
so please repeat that. Sir, please repeat that question, sir.
Which-
Whatever he is asking.
So no, he's saying for conservative field curl will be 0 actually. That means closed line integral is 0. We have to start with closed line integral because that closed line integral will define as a work done in moving some charge or something in case of electrified. Closed path. Okay. We shall see that one.
I had one word again.
Yes.
Solenoid. Solenoid.
Solenoidal field.
So divergence will be.
Solenoidal field will have curl non-zero. Yes, after what you call dealing with this curl, divergence, gradient, we have started with gradient, isn't it? So then divergence, which is equal to, how did we define? Volume density of outward flux, isn't it? Or it's a measure of how much vector field diverges from a point in question, isn't it? And curl, we have defined that one as a, circulation per area, isn't it? And it shows how much vector field curls around a given point in question, isn't it? And gradient helped us to find different derivatives, am I right? So directional derivatives and all. So these are the things that we have seen. Okay. So yes. Now we shall proceed to this product rule. Again, whenever you have so these rules of this so derivatives and all. Okay. Whenever you define derivative, you have additions, and multiplication and quotient rules, isn't it? Like that, very exactly equivalent to our ordinary one variable calculus. Okay, we have to define some rules here. Okay, so he's going to write that one as a product rules. Okay, let me note only some of those rules. Okay, only some of those rules. Later we shall come back to this set of rules whenever we need, okay, in future, because even though we list out those rules, we may not remember, isn't it, unless we apply those rules. Okay, so that's why again one of the simple rule that I can quote: if you have two scalar field, okay, f and g, okay, you have addition of those two scalar field, and if you take a gradient of that one, is that okay? If you take a gradient of that one, so that's equal to gradient of f plus gradient of g, isn't it? I hope you can deal with this kind of rules. This seems to be very obvious, isn't it? Because it's a kind of derivative operator, so that's why it will follow. We can call it as a linearity property, isn't it? Now similarly, look at here, in case of curl also, you can do like this, am I right? I mean, I think we have done that one in case of divergence and curl and all, isn't it? I think so. In case of divergence, del dot a plus b, I hope I can write like this: del dot a plus del dot b. So check this out. Anyone? Yes, we can write like this. So similarly, curl of addition of two vector field, okay, so that's equal to curl of a plus curl of b. Is that okay? So curl of a plus curl of b. Now so there are so three more rules that he's going to note on here. Again, that's also obvious. Okay, suppose if you have a gradient of some scalar into some vector field, some constant into scalar field, constant into scalar field. So usually I call that one as a scalar, am I right? Constant, whatever I have multiplied earlier, I called it one as a scalar. Now you just name that one in a different way because we have scalar field here, isn't it? Some constant into scalar field, suppose f as a function of x comma y comma z. Is that okay? This is scalar field, this is a constant multiplied to that scalar field. Again, should I go back there? Vector fields add like a vector. Scalar field. We define scalar field. Suppose temperature of the room and all, isn't it? How did I define field? Yes. Now look at here. There is a scalar. Again, don't call this one as a scalar now because it is quite confusing. Call it as a constant k. Okay. So you have a scalar field multiplied with a constant k, and you want to take a what you call gradient of the the product. So that's equal to, you can take k outside. You can take gradient of that one. Am I right? Because I hope this is very obvious for you, these things, okay? So similarly, if you have a constant k multiplied with a vector, okay? If you want to take a divergence, okay? So you can take that k outside, you can take divergence of a. These are obvious, isn't it? In case of derivative also the same thing happens, isn't it? So what I am saying here is, don't call it as a scalar, call it as a constant multiplied, okay? Because this is also scalar, we call that in a scalar field, isn't it? We call this in a vector field, isn't it? So similarly, curl of a vector field. Del cross some constant into vector A, okay? So that's equal to, you can take that constant outside, you can take curl of vector field A. Is that okay? There are a lot of rules like that. Let me, let me give you one more rule here. Is that okay? Let me rub out this one. One more rule here. Del of, so gradient of, so product of two scalar field. These f and g are scalar field, okay? So gradient of that one. So that's equal to, you can take f outside, you can take gradient of g, okay? Plus you can take g outside, you can take gradient of f. I hope this also ordinary derivative product rule, isn't it? And there is one more, he has written for, divergence, okay? Del dot, some scalar field multiplied with a vector, okay? Scalar field, not a constant. If it is constant, you can take it outside. If this is also variable, so derivative should be taken, isn't it? Are you getting my point? A scalar field multiplied with a vector field. Is that okay? So, I think this rule we are going to apply, okay? This rule we are going to apply. So, put a star mark, somewhere we apply this one, okay? We can take f outside and we can write del dot vector field A, okay? Then we can do like this, A dot, vector A dot, gradient of f. Obviously, should be scalar. So these are obvious for you, isn't it? But look at this one. This is one is scalar field. Write down scalar field. Other one is vector field. And I think you better to remember this one. And del cross, okay? Del cross A cross B. I think we are going to use this one also somewhere in the future, okay? Del cross A cross B. Del cross A cross B. Wait a second, not del cross, del dot A cross B. Later I'll go for del cross A cross B. I'm writing only some of the rule that he elaborated, okay? Not all rules. Again, we will come back to this list whenever we need, okay? Because right now, if you are not applying, you will not remember, okay? Del cross A cross B, this is required, okay? B dot, del cross A, speak out, divergence of A cross B. It should, no, it's not a triple product. Look at it, it's a kind of derivative. Again, earlier we have seen that divergence curl as a dot product and cross product, isn't it? But if you see that one actually, there's a derivative actually. Are you getting a point? It will not give you a number. Just like a scalar triple product, isn't it? You can see that one like a scalar triple product, but it is not. Are you getting my point? So look at here, and usually, yeah, so del dot A cross B, it's a kind of derivative, am I right? Divergence. Look at here. So B dot del cross A minus A dot del cross B. Minus A dot del cross B. I think this is also needed somewhere. So del cross, okay, scalar field into vector field, okay, curl of vector field multiplied with a scalar field, okay, so that is equal to F into scalar field into curl of A, scalar field into curl of A, minus A cross del F, A cross gradient of F. I don't think we applied this one frequently. Maybe in future we shall see, okay? And there is one more, del cross A cross B, quite difficult to remember, okay? Just note down this one from book, okay? It's very huge formula. It contains 1, 2, 3, 4 terms, okay? We shall see that one. If we remember, we shall take that one, okay? I mean, if we need that one in future, then we shall come back here and we shall take that one. Now let me move on to second derivatives, okay? These are all first derivatives. You can see only one del operator is there everywhere, isn't it? These are all first derivatives. Let me go for second derivatives. What kind of second derivative operation that we can do using this del operator, and what are their significance, okay? We shall see that one. Second derivatives. Okay, second derivatives. So we have started with a gradient, am I right? Gradient of a scalar field, isn't it? Gradient of a scalar. Now this is a vector, am I right? Speak out. This is a vector. You can do two things with a vector, am I right? One is divergence of a vector, okay? Other one is curl of a vector, am I right? Isn't it? These two are possible second derivatives. You can see del operator came twice, isn't it? You can call this as divergence of gradient, okay? Divergence of gradient, okay? Curl of gradient, curl of gradient, curl of gradient. So after this gradient, we have taken what you call divergence of a vector field, am I right? Do you remember? So divergence of a vector field, it's a scalar field, isn't it? It was a scalar. Now what you can do with that scalar? You can take gradient. Gradient of divergence. Gradient of divergence. Is that okay? It's a scalar, you can take a gradient, isn't it? With scalar we have taken gradient, with vector we have taken divergence and curl. So these are the three things. Now next one is we have taken curl, am I right? What is curl of a vector field? That's again another vector field, isn't it? We have seen this is a vector field, isn't it? Curl of a vector field is again a vector, okay? Now with that vector, what we have done? We have taken divergence, am I right? And with that, with any vector, just like with any ordinary vector, we have taken again curl, am I right? We call this as divergence of curl. Divergence of curl of vector field, like that we define, okay? Gradient of divergence of a vector, okay? curl of gradient of a scalar, okay? Scalar, okay? Divergence of gradient of scalar, am I right? This is a scalar. Ultimately, we have started with this one, taken gradient, then taken divergence like that, isn't it? I hope you can deal with this kind of thing, okay? Divergence of curl of a vector field, okay? Curl of a vector field, okay? Now we shall start with the first one. Is that okay? So divergence of gradient, okay? I hope if you see that one, you should be able to name what kind of derivative these are, okay? So we again, when you do this one, okay, look at here, a kind of ordinary dot product, x cap dou by dou x plus y cap dou by dou y plus z cap dou by dou z. Am I right? So taken dot product with what we have written, x cap into dou t by dou x plus y cap into dou t by dou y plus z cap into dou t by dou z. Isn't it? Now, if you take a dot product, okay, then what will happen here is x cap dot x cap 1 dou by dou x of dou t by dou x. What is that one? Second derivative. Dou square t by dou t square. Is that it? X cap dot x cap, y cap dot y cap, z cap dot z cap. If you write this one, okay, let me write it directly. So that will be dou square t by dou x square. Again, in Cartesian coordinate. We shall go to other coordinate later, okay? Dou square t by dou y square plus dou square t by dou z square. Okay? Now what we do is we are going to write this one as a Laplacian operator. Del square of t. Is that okay? Laplacian operator. Del dot del t, we call that one as del square of scalar field, okay? We call it del square as a Laplacian operator, okay? Now look at here, that Laplacian operator can be defined for vector also, okay? I mean, after you define this del square operator, what is del square t? Del square t meaning is this one, isn't it? You can define del square of, so here you can't put vector, isn't it? But after defining this Laplacian operator, okay, we call this one as Laplacian operator. I hope you know that one, isn't it? So after defining that Laplacian operator, we can take Laplacian of a vector field also. Is that okay? So that means Laplacian of a vector field means, look at here, vector field is described by three set of scalar field, isn't it? Vx, vy, vz, isn't it? So this means this one, x cap into Laplacian of x component of a vector field, okay, plus y cap into Laplacian of y component of a vector field plus z cap into Laplacian of z component of vector field. Is that okay? Can you put some brackets here? After defining this one, we can define like this actually. But don't put this v vector here, that would be wrong, am I right? You can't take gradient of a vector, okay? But after defining Laplacian operator, you can define Laplacian of a vector field like this, okay? Note down that one. I think this is required, okay? Your Maxwell's wave equation, okay? That is written, I think that can be written in terms of vector format like that, okay? We shall see later, okay? We can prove this one using 2 to 3 fundamental theorem. If you accept 2 to 3 fundamental theorem, okay, you can prove some of these, okay? Now look at here. A gradient of a scalar, am I right? This is a vector. Gradient of a scalar, this is a vector, am I right? This is a vector field. It is such a vector field that it will not have any curl, null vector. Okay? So this is a vector field, am I right? You have taken curl of this vector field. We call it as curl of gradient of a scalar, isn't it? Now this gradient is a type of vector field. It is a special class of vector field. gradient of any scalar, okay, any scalar, whatever the scalar you take, t can be any scalar, arbitrary, okay, any scalar field you take, okay, gradient of that scalar field is a strange vector field, okay, it's a special class of vector field whose curl always vanishes. We can show this one. Let me try to move on here. Let me show this one. Is that okay? That means curl of gradient is always vanishes. So next one is this one, okay, gradient of divergence, but we don't use this one, okay, much. Is that okay? Let me remove this one from the list. We don't use this one, okay. I mean, in the application side, this is not much useful, okay. Let me just remove this one. Let me not elaborate this one, okay. Again, that may have some value, okay. That's again one more vector field, isn't it? Yes. Let me move on to the next one. Divergence of a curl of a vector field. Am I right? Now look at here. Curl of a vector field is again another vector field. Am I right? So can I call this one as some vector field A? Isn't it? Now it is such a vector field that it will never diverge. It is 0. Is that okay? Divergence of curl of a vector field is always 0. Whatever the vector field you take, okay? Whatever the vector field you take. If curl exists, then that curl is another vector field. Am I right? That curl of any arbitrary vector field is a special class of vector field which will never diverge. That means that divergence is 0. Is that okay? You can show this one also later. After taking some fundamental theorems, you will be able to accept this one. Is that okay? Now there is a formula for this one. This is not 0, okay? There is a formula for this one. Del of del dot V, we are going to use this one, okay, in Maxwell theory. Gradient of divergence of a vector field, okay? Gradient of divergence of a vector field minus Laplacian of a vector field. That's why I defined Laplacian of a vector field also, okay? Minus Laplacian of a vector field, del square of V. Is that okay? This is required, okay? Del square of vector field V. We are going to use this relation in case of Maxwell's electromagnetic. These are the secondary rules. You may need to remember, I mean, these four are very important, okay? Later we shall see how to write this Laplacian in case of spherical polar coordinate, okay? That comes in so potential formalism, okay? It is to solve a Laplace equation. Laplace equation means if you have del square of some some scalar field, okay, if that is equal to 0, we call it as Laplacian Laplace equation, okay. So we need to solve this kind of equation, not with a temperature or something, with a our electrostatic potential, okay. Electrostatic potential in the region of where there are no charges, it will follow Laplace equation actually, okay. With some boundary condition, we need to solve it. So that's why that potential formalism in case of electrostatic, it is very rich in mathematics. Okay, this is a positive way of saying that. Not to say it is very lengthy in mathematics, to say it is very rich in mathematics. Okay.
We can write Laplacian as a del dot gradient of any.
Yes. Del dot gradient of that scalar. That's correct. But we don't write this one, okay? I mean, in the potential formalism, we don't write this one. But again, this is a kind of electric field for us. We shall see that one. We take divergence, we equate that one to 0. Then again, we write this kind of equation directly. Then we directly solve this one, okay? While solving this one, we don't write like this, okay? We directly solve this one with some boundary condition. If you write like this, this is a different kind of equation. This is a divergence of some vector field, okay? If you take gradient of some vector field, okay, that's a different story. That means here you are dealing with a vector, here you are dealing with a scalar. That is the difference. Dealing with a vector means vector has 3 components. Scalar, only 1 component. So that's how the difference, okay? Even though these two equations are same, but here you have three component, am I right? So we deal with this one, we shall see that one, okay? But Laplacian of a vector field can also be defined. I hope you have taken that note, okay? Yes, speak out. So shall I move on?